Assalamualaikum and good morning to the panelists, Dr. Zurati binti Muhammad Ali and Dr. Nur Afifah binti Yahya. My name is Muhammad Hazul Kushari and I would like to present my final year project entitled of Wind Tunnel Test of Short Fuselage Blended Wing Body Aircraft with Twisted Wing under supervision of Professor Dr. Wirashman Wisnu. Okay, so here are the outcome for my presentation, which firstly is the introduction, problem statement, objective, scope of work, literature review, methodology, result and discussion, and lastly the conclusion. Okay, firstly is the introduction. So blended wing body aircraft is a tailless aircraft, have a fuselage and wing design resembling a flying wing. Okay, PWB have a lower fuel consumption, maximum takeoff weight, and low operational cost. So next one is it consists of two sections, which is the center section and the outer section. So as you can see there, here is the main wing and here is the center body. So the blended area is it was blend between the main wing and the center body. So that's why it's called as blended wing body. Okay, so for my main research for this project is to analyze the BWB of twisted angle with three types of angle twisted wings in the wind tunnel. Okay, twisted wing angle means the airfoil at the wing roots was held in place while the leading edge of the wingtip airfoil was rotated in the center of rotation at the trailing edge. Okay, as you can see, here are the three cases of twisted angle from 4 degrees, 6 degrees, and 8 degrees. Okay, where the twisted angle happen is between the midsection of the wing to the wingtip. So as you can see clearly, this one, the wingtip have a different angle from each cases. Okay, so we go to the problem statement. There are two problem statements in this project. Firstly is the result of the CFD simulation need to validate to the wind tunnel test, since this project had been run before by the senior, but they use the CFD method, which the Snoopycar software. Okay, so in order to ensure that the value they get is acceptable or not, we have to use the wind tunnels method. So next one is the short fuselage of the BWB aircraft tend to stall earlier compared to other fuselage length when it reach at a certain angle of attack. For the objective, there are three objectives in this project, which is to compare the result between the CFD, the simulation result, and the wind tunnel result in order to validate it. Okay, next one is to obtain the value of drag coefficient, lift coefficient, and pitching moment coefficient from the wind tunnel test, which is the parameter of the project. And next one is to create a blended wing body aircraft model using a 3D print. Okay, so next one is the scope of work. Okay, firstly is to customize the CAD drawing of three different twisted angles to test on the wind tunnel. And next one is to fabricate the blended wing body aircraft model used for the experiment in the wind tunnel using 3D printing process. And next one to analyze the data obtained from the wind tunnel experiment, which is the parameter, the lift, pitching moment, and coefficient. Okay, so we go to the literature review. Okay, firstly is the blended wing body aircraft. Okay, it is an aircraft that combines wings and fuselage to form a single lifting body. BWB is an idea that combines a conventional tube and a flying wing aircraft. Okay, based on the research, it reducing 15% in maximum takeoff weight, 33% reduction in surface area, and 27% reduction in fuel burn per passenger mile. Okay, the blended wing body also produces lower noise and less volume tanks. Okay, from the previous research, you see the design of the blended wing body aircraft was scaled down at 35% of the original size, and and only half side of the model was used to test on the wind tunnel. So for the blended wing body was tested on the low speed tunnel with a section of 0.5 times 0.5 times 1.25 meter, and they measured the lift coefficient, drag coefficient curve, and pitching moment coefficient curve. As you can see here, the three types. There are three graphs of lift, pitching moment, and direct motion against the angle of attack. So next one is the air stall. Okay, the stall is an airflow effect that happens when an aircraft passes through critical angle of attack and cannot create lift beyond that point. As the angle of attack increases, the aircraft will decrease manually. As you can see, the figure beside here shows as the angle of attack increase, there will cause more separated flow region expand and create a large turbulence. Okay, next one is the aerodynamic of aircraft. Okay, it's defined as a force exerted on a body by the air where the body is submerged with attributable to the relative motion of the body. Next one consists of four general forces, which is the lift, drag, thrust, and weight. So we go to the methodology. Okay, firstly, it consists of three phases. First one is the phase one consists of the literature review and the preparation drawing of the CAT, and for phase two is was mostly focused on the fabrication and the experimental setup, and the last phase was to analyze the data and doing report analysis. Okay, so here are the drawing of the blended wing body. So the dimension of the blended wing body was reduced up to 24% of its original dimension. It is because to ensure that the blended wing body able to fit into the wind tunnel cross section area. So the wingspan after it was been reduced was 296.78 millimeter, and the chord length here is 176.83 millimeter, and only half side of the body was used to test on the wind tunnel. Okay, next one we go to the fabrication of the blended wing model. Okay, so here as you can see here this is the 3D print model outcome. So in order to print the model, the SolidWorks file need to transfer into STL file in order for the 3D print to read the drawing. Okay, next one is apply semi-putty. Okay, semi-putty was used to coat the blended wing body model to create a smooth surface, since the 3D print model has a rough surface and it may affect the result on the wind tunnel. Okay, so before applying the cement putty to the model, the cement putty need to mix with a thinner. The reason why we do this is to reduce the viscosity and thickness of the cement, and to ensure that a very thin layer of cement putty will apply to the blended wing body. It is also to avoid any deform in dimension or the twisted angle. Okay, then next, after the cement dry, rub the model surface with sandpaper. Use a finest grade of 1000 to 1500 for smoothing the surface. Okay, next one, after done, the model was then sprayed using a primer paint. Why we use the primer paint? Because it has a good finishing, better finishing surface, and had a coated layer. Okay, so next one is the mini turf visualization. Okay, as we can see that the mini turf was cut into 20 millimeter of length, and it was stick to the body of the blended wing body with a distance of 10 millimeter. Okay, why the mini turf visualization purpose is to observe the flow pattern of the blended wing body on every angle of attack. Okay, so next one is the wind tunnel setup. Okay, so the low speed tunnel, or known as LST1, was used for the experiment. So the dimension of the cross section, the dimension area to test the blended body was around 500 millimeter times 500 and times 1250 millimeter for the area size, and the speed we use is 30 millimeter per second, and the angle of attack was set from -10 to 34 degree with increment of 4 degree. And here are the parameter value for the blended wing body. First is the reference area, which is 0.02539 meter square, and the wingspan length is 0.2 296 and the reference length is 0.17683 meter. So for the result of this question, firstly is the lift coefficient versus the angle of attack. Okay, as you can see that the original short case which has a 0 degree of twisted angle had the lowest lift coefficient compared to the others cases which have a twisted angle. Okay, for the case 2, it reached a maximum value of 0.7784 of lift coefficient at when the angle of attack at 22 degree before it began to stall, and it is considered as the highest value of lift coefficient among the others. Okay, so in this case we can conclude that we can say that adding a twist angle able to increase the lift coefficient. Okay, so next one is the drag coefficient versus the angle of attack. Okay, for short case, original short case and case 3 had a similar trend of drag coefficient from angle of attack from 18 degree to 34, while case 2 and case 1 have a similar trend from the start until the end and only a slightly different at angle of attack at 22 degree. Therefore, case 2 and 1 shows a lower drag coefficient value than the original short fuselage and case 3. Okay, next one is the pitching moment versus the angle of attack. Okay, so you can see that all cases shows a negative slope where the pitching moment values decrease as the angle of attack increase. A negative slope implies pitching stability with the aircraft tending to nose down during the flight. Okay, for case 3, it shows the shallowest slope compared with the other cases when the angle of attack at -2 to 10 degree. Okay, the graph shows an increasing slope at 18 degrees, and after that it start to decreasing and all stall back. So next one is the lift drag versus angle of attack. So as you can see that case 3 has the highest lift drag ratio, followed by case 2 and case 1, as lastly case original short case. Okay, lift drag ratio is important to identify the aerodynamic efficiency of the aircraft, where if the aircraft have a higher lift coefficient and low drag coefficient, it will give a high value of lift drag ratio. So in this case we can see that case 3 has the highest lift drag ratio compared to the others, and some of the important is that they able to carry a large payload in a long distance. Okay, next one is the comparative result. Okay, first one is for the case 1, which is for the 4 degrees of twisted angle. Okay, as you can see that the lift coefficient result shows that the wind tunnel had a lower lift coefficient compared to the CFD value. Okay, same goes to the drag coefficient, where the wind tunnel had a lower drag coefficient compared to the CFD value as the angle of attack increased. Okay, so for the pitching moment shows that both data of the CFD and wind tunnel had a slope, negative slope, and for the CFD value, when the angle of attack reached at 80 degree, it start to increase and then stall back. Okay, for the wind tunnel, the increasing of the pitching moment started when the angle of attack reached at 22 degree, and after that it will start to stall back. Okay, next one, we go for the case 2 comparison, which is for the 6 degrees of twisted angle. Okay, as we can see that both of the lift coefficient and drag coefficient shows a similar pattern as the case 1, where the wind tunnel had lower lift coefficient and drag coefficient compared to the CFD value. Okay, so next one we go to the pitching moment value graph. Okay, so we can see that both case of CFD and the wind tunnel have a negative slope, and they also had the same angle of attack at 18 degree, where both of the value had both of the case had an increasing at when the angle of attack at 18 degree. Compared to the CFD, it has much higher increment compared to the wind tunnel. So and both of the case shows a decreasing, or the pitching moment be, become decreased at the angle of attack of 26 degrees. Okay, next one is the comparison for case 3 of 8 degrees. Okay, as you can see that for lift coefficient and drag coefficient, it shows a similar pattern as the case 2 and case 1. Okay, for the pitching moment coefficient graph, both case had a negative slope until it reached a certain angle of attack and start to rise up. Okay, for the wind tunnel, when the angle of attack reach at 14 degree, it start to increase, the pitching moment start to increase and start to stall back. Okay, for the CFD value, the increasing of the pitching moment start when the angle of attack reach at 22 degree. Okay, lastly is the miniature visualization. As you can see that when the angle of attack at negative 10 degree, the miniature show a nothing change. As it reached to 14, the pattern start to change at the wingtip of the aircraft, and as the angle of attack increased to 22 to 34 degree, the pattern start to change for the whole aircraft wing, where this mean that the flow separation is become larger and the turbulence also increases, causing the aircraft to stall. So in conclusion, the speed used was 30 meters per second for all the cases. The aerodynamic characteristic, the drag coefficient, lift coefficient, and pitching moment coefficient was obtained, and the result were able to compare with the CFD result and the original short fuselage of the BWB. Okay, based on the comparison result, we conclude that the CFD and wind tunnel values were quite different. The CFD tend to have a higher lift than the wind tunnel value for the lift coefficient, and the wind tunnel had a lower drag than the CFD value for the drag coefficient. Okay, for further investigation, it can be carried out to identify the aerodynamic behavior of the angle on different speed, since this project is only focused on one speed, which is 30 meters per second. So that's all from my presentation. Thank you to the panelists and to the viewer that watched my video. Here I have put my numbers and email if there is any question regarding to my presentation of the final year project. So thank you and goodbye.